So good morning, everyone. I guess all of you have met me already during the past couple of days. My name is Isabell Bludau, and I'm a PhD student in the Ebersol lab here at ETH. And today I'll give you an introductory lecture to the software MSstats, which is a tool to actually derive relative protein number estimations from the MS-based proteomics experiments. So the software is developed in Professor Olga Witek's group, who just gave you some biostatistics lectures yesterday. And the main developer and maintainer is Mina Choi, who also helped me quite a lot with setting up this presentation for you today. So what is MSstats generally? So it is a statistical tool to derive relative quantifications of proteins and to estimate differential expression of those between different groups, for example, treatment versus control samples. And it also includes several methods to do a quality control of your samples and to design future follow-up experiments. So MSstats is available as an open source package which can be downloaded from the MSstats website or from GitHub directly. And it's also available in Bioconductor, and what we will use later on is the application of MSstats from within Skyline as an external tool. And you will do this in the tutorial just after this lecture. So today I will try to walk you through the different steps of MSstats processing. So first of all, before you do your MSstats analysis, you need to perform an experiment, which includes designing an experiment, and I will talk a little bit about experimental designs that are compatible with the MSstats analysis, and about the format that you need for MSstats input. And then we'll talk about the actual MSstats processing steps, which include data processing and quality control, followed by a group comparison where you actually get those differentially abundant proteins. And finally, you can also use this option to design follow-up experiments. So MSstats is compatible with quite a lot of different experimental setups, so you can use DDA data, SRM or PRM data, and also DIA acquisition data sets, and it is also working on label-free as well as on a label-based approach. And the nice thing is that it can really handle a lot of very different and also very complex designs. So you can have multiple different conditions, you can analyze time course experiments, and also paired analysis is possible. What is currently not supported are multi-labeling experiments, for example, SciLag or iTrack, but I think there might be something in development and maybe released in the next couple of months or years. So now come to the data that you need for MSstats. So after you acquired your data from the mass spec instrument, you get your results from any spectral processing tool. What we did in the last tutorial so far is using Skyline to get to do the peak extraction and get intensities for all the different fragment ions. And then what you should get for MSstats is a tabular CSV format, which includes following information. So here, this is an example head of a file that can be read by MSstats. So what you need is the protein name, the peptide sequence, and the precursor charge. And then in cases where it's available, you should provide the fragment ion and the product charge. In DDA datasets, you usually don't have this information, so you can just set these to an A. For labeling, you have this isotope label type column where you select heavy or light. And in cases where you have a label-free workflow, you just can put a light for all of the samples. And for the different comparisons, you want to specify the conditions, the biological replicates you have, and the run ID. And the final column is the intensity value, which can be either the the height of your intensity, or in most cases, or in Skyline, it's the area under the curve of the intensity peaks. So after you got this table from your data processing, initial processing, then you can import the data into Skyline and into MSstats, sorry. And the first step is after the import of the data, a log transformation is performed in order to make fold changes more feasible to calculate and to deal with the data. And in a second step, the intensities are normalized. So when you have unnormalized data, there's an example here. So you have the log2 intensities on the y-axis and the MS runs on the x-axis. And in this case, you had a label-based workflow. And on the left-hand side, here in green, you see all the heavy references. And on the right-hand side are the endogenous intensities. And you can see that you don't have any big outliers between the runs, but the median intensities are a little bit different across the runs. So when you do an equalization of the medians for normalization, the reference peptide intensity distributions are corrected so that you get an equal median intensity value across all the MS runs, and the endogenous intensities are shifted according to their labeled reference. If you don't have this label-based workflow, this normalization is just happening on the endogenous peptides. So when you do a quantile normalization, this is another option. You don't only normalize or equalize the medians, but you equalize the entire intensity distribution. So you can see here that all the distributions are the same for all the heavy references. A fourth option is to use global standards for normalization. I think Tina already touched a little bit on this in her talks on Monday and Tuesday. And in this case, you just select a number of endogenous proteins which you expect to have the same intensity across all your runs, and use those for the normalization. So there are a couple of considerations that you should keep in mind when you select the normalization method, because the different normalization methods have certain assumptions that need to be met. So for a median and quantile normalization, you really expect that the majority of your proteins do not change in abundance across all the samples. So this is only true in cases where you have a heavy reference standard, or if you have protein standards in your sample, or if you have, as I said, the majority of your proteins constant. And this would, for example, be the case when you have a lot of different proteins measured, as in a DIA setting, and you have a lot of proteins, a lot of peptides per protein, a lot of transitions, and then you can assume that the majority of those proteins are actually not changing. So if you have a setting like this, it's an example SRM data set where only a couple of proteins have been measured, and you see that there's a shift in intensities across the different runs. But this is actually the biological signal you have. So if you do a normalization, as this here, like the equalized median normalization, you will get rid of your entire biological signal. So just keep this in mind when you select your normalization method. And MSstats gives you as an output a quality control plot, which visualizes the normalization. So you can generally check if there are any potential systematic biases where some runs are still out of the normal range. And you could just have a look at how this performs. So what is usually done in the next step after transformation and normalization, you take all of the transitions for a protein to do relative quantification and differential expression. But in cases where you have a very large data set and you don't have you don't expect like super high quality for all of your transitions, you probably want to consider to only take a subset of your features and take out the features where you have an interference. So there's an option in MSstats, which is also available in Skyline, to do a feature selection. And as a first step for this, you want to detect features that have an interference. So as you hopefully recall from the previous sessions, nice peaks with like good without any interferences, you would expect conserved relative intensities for all the transitions across different runs, and you have like this, the peak area plot in Skyline should look roughly like this. And this is also what you did for the peak selection manually. And if you can somehow convert this into a different visualization where you have the intensities on your y-axis, and these are the MS runs, and here you see the intensities for the 4 transitions of one peptide across all the MS runs, and they all have nice and parallel features. However, if you have an interference signal, the relative intensities are not conserved across the different samples. So in this profile plot, you see that there might be some outliers which are not parallel to the other features. And so with this methodology, MSstats tries to quantify how parallel the features are. And this is done with a simple algorithm. So in a first step, the fragment ion intensities for each peptide are summarized in an outlier stable way. So here you see again this profile plot for 4 transitions of one peptide, and this red line here visualizes the summarized intensity profile. Then you can estimate the degree of interference by the variance of the residuals. This means that you calculate the difference of the summarized peptide intensity to the measured fragment ion intensities, and here you can see that all those arrows are roughly the same size, so the variance between those residuals is very small, and thus there's a low degree of interference. Here you see that the difference to the summarized value is varying quite a bit between the different runs. So there you have a high variance of residuals and thus a high degree of interference. So MSstats goes ahead and removes the features with the highest degree of interference until you have no longer much of an improvement. And then you can see here this noisy feature was removed, and you have very nice and parallel lines for the remaining ones. So this is just the data set, an DIA data set, where this high quality feature selection was applied. So before the feature selection, you see here we have actually 8 proteins, 8 peptides for this protein, and each peptide has several transitions. So all the peptides have a different color, and the different features for each peptide have a different line type. I think you cannot really see it here, but if you look at it in a more closer way, you can see this. And what happens during the high quality feature selection is that you remove those outlier transitions, and this gives you much more equal profiles, and you get rid of those interfering transitions. Are there any questions to this so far?
Just had a question about the QC plot thing. So which features are you looking at there? This
is just a box plot of the distribution of intensities for all the features, so all the transitions that are in this run.
Okay, that's all.
Okay, about the feature selection.
Yeah.
So like 2 slides ahead.
This one.
Yeah. So it's always done based on you make like a summed profile of all transitions and then look how all the transitions relate to that.
Yes.
But it's done for each peptide separately, right? Because
Yes.
in XPlot you had all of them in one, but still the comparison is always between the peptide and its corresponding transitions, right?
Exactly.
Okay.
Level of MS1, like, can this the same thing can also be done on a level of MS1 when you do data-dependent acquisition, or it cannot be transferred so nicely?
Yes, I think this also can be done for MS1.
Would you go back to look what's happening with that one and maybe try to change the window for the transition?
So this is something that is also very nice. For example, if you use MSstats from Skyline, you can always go back. If you look at your profile plots or the QC plots, you can have a look if there are some strange patterns in there, and then you can go back to your Skyline document and have a look at those peptides or transitions and see if there's something probably gone wrong with the peak picking or with the boundaries, and then redo your analysis and check if you get more sensible results. Okay. After the feature selection, there's an additional step. So when you have a data matrix, you have already seen that there are sometimes some missing values where you cannot really make an intensity estimation because you don't find a peak. So those missing values can have two different sources. So the one type of missing value would be a random missing value, which is due to technical variability. And the second type of missing values would be censored values, where the intensity of your feature was just below the limit of detection in your instrument. So those censored missing values can be imputed from a model or replaced by a constant low number value. And in MSstats, what's usually done and what's also done from MSstats in Skyline is to replace those missing values by the minimal value for each feature and use this as an estimate to get a full data matrix. So after you have done all those, yep, okay.
Is there like a smart way that the MSstat is using to distinguish between this random and censored missing values?
This is actually done before that. So the processing tools that you use before MSstats is usually distinguishing between those two types and sets the values either to NA or to 0. And depending on whether it's NA or 0, MSstats decides whether to impute the value or not.
And what if it's not? Because max quant, I believe, is not, for example.
Then you can't really do a lot, right? So I don't know, maybe, Olga, do you have a comment to this?
Yeah, so Skyline distinguishes that, but max quant doesn't. So then you have two options, essentially. View everything as censored or everything as missing at random and do a sensitivity analysis to see how your conclusions depend on one of the two approaches.
So after you performed all of these different transformation and normalization steps to get your data as clean and complete as possible, you come to the first step of modeling, actually, which would be a run-level subplot summarization. And this sounds a little bit complicated, but what it's basically doing is estimating the relative abundance for each protein in each run. So subplot means that we do not consider the entire experimental design for this, but we only consider the features and the runs. So this means that if you look at your table you have, here you have the different conditions. Within each condition you have different subjects, which are the biological replicates, and then you have the runs, which are the technical replicates of each subject. And here, these features are the different transitions for the protein you're looking at right now. So for the summarization, you only consider the run independent from the experimental setup and the features of the protein of interest. And what MSstats does is taking a very stable median polish, which is called Turkey's median polish, which is the robust parameter estimation method, which basically takes the medians across all rows and columns and then this normalizes the data in a very outlier independent way, so that you can get good estimates for you have a normalized data matrix after this median polish, and you can summarize the values for each run in a very stable way, so that at the end you only get one summarized protein intensity value for each run. And the summarization step is visualized also in the profile plots that you will get out of MSstats. We've already seen this for the feature selection, so you have the log intensities over the MS runs, and here you see this for all the peptides of the protein and all the transitions. And here on the right-hand side, you have the summarized intensity, which is marked in this red color, and all the single transitions that contributed to this summarized value are in gray behind. So you can check this if this corresponds to your, like, this should actually roughly represent what you can also see in this transition level plot. And these profile plots are also nice to check for potential sources of variation. For example, if you didn't consider a high quality feature selection in your first analysis round, and you then see that you have some interferences in this profile plot, you can still go back and do the analysis again and do a feature selection. And what you can also check is for missing values, which is the biggest concern probably in DDA data, where you just don't have any values for some of the runs. So the last visualization that MSstats does for this first processing step is the condition plot, which represents the mean plot of the log values or the heavy to light ratios across the different conditions. And this can show you potential systematic differences in the intensities between those conditions. And the error bars here are the confidence intervals with 95% significance level. So here you see that this was a swath experiment that you will also perform later in the tutorials tomorrow, I think. So here you have 3 wild type subjects and 3 mutants, and this is the mean intensity with the confidence interval for those 2 conditions summarized. So once you derived at the complete table for each protein, you have this relative intensity values for all those runs. You can actually go on with the group comparison. And in this step, you apply a statistical model, which is a linear mixed effect model, to consider now all the different conditions and biological replicates. And here, this is now the whole plot design. So those summarized values are the ones that you got from the summarization step. And in this linear mixed model, you now model for the condition and the biological replicate in cases where you have a group comparison. When you want to do a time course experiment, MSstats applies a slightly different model. So the factors are the time and the subject, and a combination of those two, because you always have this a single subject in the different time points, right? So what you get out of this linear mixed model analysis is basically the answer to 2 different questions. So the first one is there actually a difference in abundance between the subjects in condition A and in condition B for a specific protein, and this is the log 2-fold change. And the second question is if this change is actually significant, and the value that provides you the answer is the adjusted p-value, which is the probability that your conclusion is actually wrong, and this p-value has been adjusted for multiple testing. So what you can see down here is an example output table from MSstats, where you have the protein identification, the label, which means which specifies the two conditions you are currently comparing. Then you have the log 2-fold change, some values which are concerning the linear mixed model, and for you important again is the adjusted p-value. And those results are very nicely visualized in volcano plots. So those volcano plots basically plot the log 2-fold change on the x-axis with 0 at the center, and the minus log 10 adjusted p-value on the y-axis. So the statistical significance is increasing from bottom to top, and the so-called the practical significance, which is the biological signal you want to effect you want to observe, is rising in significance from the middle to the sides. So the significantly upregulated proteins should have a high log 2-fold change and also a very low adjusted p-value. So those would be up here in the upper right corner. And the significantly downregulated proteins are in this upper left corner. If you have multiple,
I'd like to ask, maybe you can comment how you calculate p-values and what statistical tests would you choose for different experiments?
So the p-value is basically calculated from those linear mixed models that are built in this concept, right? And then you can make an error rate estimation similar to a t-test between the models that you for the models that you fitted. Maybe you, Olga, can comment on this again.
Could you bring the slide back with the models? Yeah, exactly. So what you actually do, you describe in this model all the sources of variation in the data, and you see that you have a condition term in the first part, or you have time in the second part. So this actually is multiple parameters. So if you have, let's say, 5 conditions, you will have 4 different terms there. And so then if you say, I want to compare condition 1 to condition 2, you pick out the specific parameters from this model, and this give you the estimates of change between 2 conditions, and you use the rest of the model to derive the standard errors. So it's kind of the same procedure we talked about yesterday, but it's more general now because we have more sources of variation. And at the end, it's the same thing. You have the signal from the model divided by the standard error from the model. If the null hypothesis is true, it's either student distribution or normal distribution, and you have p-values from that. So it's a generalization of a t-test, but it uses all the sources of variation that we describe here.
Okay. So if you have multiple different conditions that you want to compare, MSstats can also provide you a visualization which basically shows you all the different comparisons that you did. So the way this is done is by producing such a heat map, and what is done for this is that the p-value is has a specific sign dependent on the log 2-fold change which it has. So in cases where for proteins where you have a negative fold change, the p-value gets negative, and in cases where you have a positive fold change, the p-value is positive. So what you can see here are the different comparisons. So this is a time course experiment where you have here compared time 1 to time 3, and you have a certain number of proteins on the y-axis, and you have some of them are upregulated in red, and the downregulated ones are in blue. And then you can see that if you compare time point 1 now to time point 5 or time point 7, you get more significantly up and downregulated proteins. And the final visualization would be the comparison plot, which represents the log log-fold changes for multiple comparisons for each protein. So here you only look at a specific protein and have the log 2-fold change on the y-axis and the different comparisons here. So what you can see is that between the first 2 time points there's not such a big change, but when you compare time point 1 to time point 7, you have a very high log 2-fold change. Okay, now we get to the last step in the MSstats processing modules, which would be the design of future experiments, and this is done based on a power analysis. So the goals of this power analysis would be to use the current information that you have from the data set to estimate power of your analysis, or also for future analysis, and even more importantly to estimate the required minimal sample size for getting a sufficient statistical power in follow-up experiments. So the parameters that you have in this power, or need for this power analysis, are first of all the power or the sensitivity of your analysis, which would be the probability of detecting the effect. And this is a usual cutoff would be 80%. So this would mean that when you have all the if you have all the cases that are a true effect, you would only see 80% of those. The sample size is the number of biological replicates, and in a power analysis you can choose whether you want to calculate the power or the sample size. So one of them needs to be specified and the other one is getting calculated. Then you need to specify the false discovery rate, which is the probability of rejecting the null hypothesis even though it's true. A common cutoff would be 5%, and what you need for the power analysis is the variance in your data. So this sample variance is estimated from your current data set. The last parameter would be the effect size, which is the minimal deviation from the null hypothesis that you still want to be able to observe, and this would be the anticipated fold change. So if you want to derive a statistical power estimation, you need to specify the number of replicates you have in your sample and the desired fold false discovery rate. And then what MSstats gives you is a plot where you can see the desired fold change with the power estimation on the y-axis. And you can see in this case, for this specific data set, if you want to observe a fold change of 1.1, you actually only have a statistical power of less than 10%. However, if you go up with the fold change and say, okay, I also accept just to be able to see a fold change of 1.2, you get up to a statistical power of more than 90%. And if you look at sample size estimation, you again need to specify the false discovery rate and the statistical power that you want to achieve. And you can see that if you want to actually see this desired fold change of 1.1, you would require at least 10 biological replicates for a data that has approximately the same variance as the data set you've been measuring right now. So this is so far for the MSstats workflow. Are there any questions to the workflow right now? Okay. So one very nice thing about MSstats is that it's available in Skyline and that it can be automatically installed as an external tool and is then available in the tools section. And I hope that all of you managed to install it on your laptops already. You have the 3 different modules of MSstats, which can be done from within Skyline, and the things you need to specify are the normalization method, which would be this either no normalization or the equalized medians, the quantile normalization, or you select a specific set of global standard proteins. Then you need to select how to deal with missing peaks. This is just a way. It's not so important from within Skyline, because Skyline usually creates quite complete tables, and you get NAs for everything where you don't have a value. But you can check this just to be sure that you don't get any incomplete rows in your data set, which would make problems in the analysis. And then you can choose if you want to do a high quality feature selection. And so in cases where you don't have any good features, a peptide and also an entire protein can be removed from the data set. So in case you want to have to allow MSstats to remove an entire protein from the analysis, you can also check this. However, this is only recommended for DIA data where you really have a lot of proteins measured, and so you don't lose the one specific one of your interest, right? If you do the group comparison, you still need to specify all those normalization and regarding parameters, because this is just done automatically again for each analysis to make it more independent. But additionally, you specify the name of the comparison and the control and comparison group. And then you will get the according results. And if you want to design future experiments with MSstats, you can select if you want to calculate the sample size, estimate the sample size or the power, and you need to specify the false discovery rate. So one thing which I already mentioned a little bit earlier is that one very nice thing is that you can go back and forth between MSstats and Skyline. So in cases where you see problems in the profile plots, for example, you can go back to your Skyline document and check on the specific peptides and see, okay, there's actually been a problem with the retention time, and also maybe the peak intensities are not so correct, and you finally figure out that there's actually a wrong pick being picked by Skyline. So a final comment would maybe be from the side that you need to make sure to be aware that different experiments require different statistical methods and models. So this is just a visualization of how different data sets from different acquisition methods look like. So if you have a DDA experiment, you have quite a lot of peptides measured per protein. However, you have this holy data, right? So you don't have a measurement for all of the runs. If you have SRM data, you only measure quite a few peptides per protein, and but you get very complete and high quality data sets usually. If you have DIA data, the thing looks much more messy, so you have a lot of peptides, a lot of transitions usually, and you might have a lot of interfering signals within your transitions maybe. So the recommendations for the parameters would be for regarding the normalization, global standards are always a good idea using reference peptides. For DDA, you should not do an equalization of any medians in messy data where you don't have any references. For SRM, you can do an equalization of medians. We would not necessarily recommend to do a quantile normalization where you have not enough proteins where you don't expect a change. This would probably be an overfitting. For DIA, you can most likely, if you have a large enough data set, do a quantile normalization in this case. Concerning the high quality feature selection, this is especially recommended for DIA for quite obvious reasons, I guess. For SRM, it's also very good when you have quite a large data set, and to allow the removal of the proteins is probably only recommended for DIA, because in SRM you're usually very interested in the proteins you selected from the start, so you don't want to get rid of this. And for DDA, this would basically result in a 50% removal of your proteins. So with this, I'd like to thank you for your attention, and I'd like to really thank Mina for helping me with this presentation, and Professor Olga Witek and her group, and everyone who also contributed to the figures I just shown you and the concepts behind. And yeah, if you have any questions, please feel free to ask.
So you can input also max quant results. So those would be peptides, not even charge state dependent precursors, let's say same peptide, charge state 2 or 3, but it would be peptides with their intensities, which would be area under the curve or whatever max quant gives you. And then also, of course, there has to be the proteins. So MSstats would just do the statistics for you per protein group on the peptides that is given.
Exactly. Yeah. So there are, I think, reformatting opportunities to get from the max quant results to the tables.
No, we actually have a converter from max quant to MSstats on the MSstats website. So it takes the raw data and it takes the most low-level information possible. So I suggest that you use that as opposed to like the summaries that max quant gives.
So most raw data, what do you mean by most raw evidence file?
Yeah, I believe so. So this is what you could yeah. So I don't remember the exact details, but we spent a lot of time taking as much low-level information as max quant would give you. So I don't know exactly what the file format is, but you can double-check its all information on the MSstats website.
I guess maybe one difference is so max quant is doing like the imputation differently than MSstats, right? So they have some simulation. Do you have a comment about the difference between these, or does it make a big difference? I mean, they seem to say that having a distribution that represents the noise and then sampling from this is for some reason useful.
Yeah, you know, I don't know all the details of what they do. Yeah.
Maybe I can comment on this. So max quant doesn't do any imputation; it's per se, and then you can choose whatever you like. You can put just one value for everything, or you can say I want to impute from the noise, which when you shift your normal distribution towards the noise and say whatever width and so on and so forth. So all these options.
But this on top you can also features you can do it on the you can import the evidence TXT and do it. Yeah, it's up to you. You don't have to take the protein groups. You can do it.
Coming back to max quant, then I guess you take not the raw intensity, not LFQ, so kind of pre-processed by max quant.
So I just really don't know the details of max quant processing, so I think Mina would be a much better person. But generally speaking, we want to take in the data which are as little processed as possible. And the reason is that this summarization, they already often take advantage of some summaries of the data over all the runs or all the features. And the fundamental assumptions and methods is that the individual intensities in runs are independent. And if you do this kind of normalizations with LFQ or other things, these assumptions become violated. So as I say, Mina would know much better than I do in terms of the formats and all that, but we try to get to as little pre-processed data as possible to work with that.
It's a small question. The volcano plot that you showed us, one of the caveats with t-test is that it can suffer a lot from very small change, but very reproducible and give you highly inflated p-values. And that's why there is a lot of this curvature of the significance that is done in the t-test field. So in this example, there are quite a few proteins which had extremely low fold change but very high p-values. I'm a bit surprised to see those. I would say those in the middle that are close to zero or very close to zero and yet have very high p-value. So here, if you don't filter for the fold change, you would pick up those as candidates or biomarkers and so on. So how is this not taken care of, but how is it considered? Those very small fold change, very high reproducibility.
Go ahead.
Well, I don't know exactly which data set this is, but generally, you know, this is what we talked about yesterday, right? The fact that the p-values themselves, you shouldn't take them like as the last word of like the most stable and so on, right? So clearly, depending on the number of replicates and depending on kind of how things fall, it is very possible to have small fold changes with small p-values, and then next time you do it, it will be changing. So we recommend two cutoffs, right? One is the statistical significance cutoff, this is the horizontal line, but then also the practical significance cutoff, where you actually use larger fold changes. But for which reason here specifically it came up like that, it really depends how many replicates you have, how many features you have, right, how consistent they are, and all of that.
Last one, I promise. Coming back to this data imputation, would it make sense to, let's say, set some threshold to try to distinguish between this random and censored missing values? Let's say if my all the other values are within the noise, then probably I have a missing value because it was just at the level of detection, so it was just randomly not detected, and then I could impute it. While if all the others are very high, then probably this is just because of DDA, it was not detected. Would it make sense to try to set such thresholds and to the imputation?
Yeah, well, there are many ways that you can do it. So for example, Skyline, if Skyline sees that the peak is truncated, clearly it will be missing not because it was low detection, but because the quantification is unreliable, right? And so it will be a missing value. If it's a really clear signal, right, very low noise and there is no peak, then probably it's because the analyte is absent, right? So Skyline kind of makes decisions along these lines. Now, if you're not using Skyline, you're using MaxQuant or something else, you would have to make some kind of other choices. So, but we think that for this, you really need to look at the raw spectra as opposed to just work with the data. And so that's why all we can offer is two options, right? Assume either one or the other, or edit your data to have 0 and NA. Like, so maybe I should just kind of clarify that there are two ways, at least two ways to use MSstats. One is through Skyline, but the other is in R. And if you're using MaxQuant, you will have to go through R, right? And then you can just edit your data set with any other criteria. But just in light of the discussion, yesterday's discussion, so what you really want to do is to define this protocol before you see the data. So you really don't want to start manipulating that until you get the result you like. So.
I would like to ask regarding the same comment. So once you have a truncated peak, which is unreliable, but you know that the intensity is in somewhere in some range. So that is kind of much better than having 0 for p-values, because that would be
NA.
Yeah, would be an A. But if you know that's not an A, and that's then your p-value doesn't suffer that much. Is there a way to kind of account for this?
Well, as I say, so anything you do to your data, if you don't have the actual measurement, is the assumption, right? So there ways to do it. You can try to fit the curve to your peak and estimate the full area under the peak. You can leave it missing, and if you have more replicates, it will just use the other replicates for that. You can do all kinds of things. So, as I say, I would rather keep things simple, because it's easy to overdo this, you know, in some kind of cases which are not exactly clear, right? So if the peak is truncated, you know, before the apex is one thing, but if it's truncated after the apex and you need to fit the full curve, you know, it becomes difficult to generalize. So I would probably keep it simple there. Yeah.
Okay. Thank you. Let's go on with the MSstats tutorial.